Hey you guys, this is Mr. Millings, and in this video we are going to learn how to do some calorimetry calculations. And before we start learning some calorimetry calculations and how to do them, here's a little disclaimer for you. It says right here
that prior knowledge of the topics listed below is necessary before watching this video.
and I recommend that you first watch the video on specific heat capacity and then watch the video on calculating thermal energy using this formula right here, Q equals Cm delta T, before beginning this video. So here we go. Let's first start talking about what is calorimetry. So what is calorimetry and how does it work? Well, it says right here that calorimetry is the process of measuring the amount of heat exchanged between two objects that have different temperatures. And to do some simple calorimetry, we can use a styrofoam cup as a calorimeter. A calorimeter, people, is an apparatus used for measuring the amount of heat involved in a chemical reaction or other process. So in a typical high school laboratory or experiment, you will probably end up doing a coffee cup calorimeter lab. And coffee cups, styrofoam coffee cups, generally make very good calorimeters because, as we know, styrofoam has a tendency to trap heat. It is a good insulator. And so when we're looking at performing experiments where we don't want heat escaping into the atmosphere, we can use a styrofoam cup as our calorimeter. So what is calorimetry? Well, it says right here once again, it's the process of measuring how much heat is exchanged between two objects that have different temperatures. So let's suppose we have an unknown sample of metal. And all we know about this metal is the mass of this metal, right? Let's suppose we knew the mass of this metal to be like 50 grams. And we know that the temperature of this metal is also 120 degrees Celsius. And so what's going to happen if we put this very hot piece of metal in a given amount of water? Let's suppose here we have, say, 125 milliliters of water at 10 degrees Celsius. Well, if we think about it, if we transfer a very hot piece of metal into some very cold water, what is going to end up happening is that the very hot metal is going to transfer some thermal energy, right? Some of the Q, or thermal energy, is going to be released from this piece of metal. And if we think about it, what's going to end up happening is that this water here is going to absorb thermal energy from this piece of metal right here. So Q here for the metal is going to be negative because it's going to release heat, and Q here for the water is going to be positive because it's going to absorb heat. And if we assume that our coffee cup calorimeter is doing its job, then none of this energy that is being released by this metal here is being released into the surroundings. It's all being released into the water. So what does that mean? Well, that means that negative Q equals positive Q. That means that the amount of thermal energy that is released by this metal here is equal to the amount of thermal energy that is absorbed by the water. And we can begin to measure the amount of energy that is released by the metal and absorbed by the water by taking a look at the temperature differences between these two substances. And that is exactly what calorimetry is. And so in a standard coffee cup calorimetry lab, this is what you're doing. You're trying to figure out the specific heat capacity of this unknown object using a formula after you've obtained the amount of thermal energy that was released or absorbed, and after you obtain the masses of the water and the starting temperatures of the water and the metal here. Okay, so that is what calorimetry is. So let's take a look at a few example problems and apply this concept to two different sample problems. In this first example, it says if 45.9 grams of solid aluminum at 356 degrees Celsius with a specific heat capacity of 0.900 joules per gram degree Celsius is added to 253 grams of water at 15.2 degrees Celsius, then what will the final temperature of the water be? So when we come across these calorimetry problems, what I like to do is draw a little picture so I can see what's happening. And so what's happening here is that we have 253 grams of water at 15.2 degrees Celsius. And what we're going to do to this is we're going to add a piece of aluminum to this, right? We're going to add 45.9 grams of aluminum at a really high temperature, 356 degrees Celsius. And what we're being asked to calculate here is the final temperature of this water in degrees Celsius. We want to know what the final temperature of this water is going to be. And so if we think about it, here's what's going to end up happening. When we put this hot piece of aluminum in this cold amount of water here, this aluminum right here is going to lose a certain amount of energy. So Q, the amount of energy, is going to be negative. And if our calorimeter here works correctly and traps all the heat in, then if we take a look at what's happening with the water here, the water is going to absorb all of the thermal energy that the metal loses and will be positive. And so if we think about it, negative Q equals positive Q. The amount of thermal energy that is lost by the metal should be equal to the amount of thermal energy that is absorbed by the water. So when we say negative Q equals positive Q, that's what we mean. We mean the amount of thermal energy that is lost by the aluminum is going to be equal to the amount of thermal energy that is absorbed by the water. And in an earlier video, we learned that Q equals C times M times delta T. So what we can do now is wherever we see Q, we can replace that with this formula right here. And that's what we've done. We've replaced Q with C, M, and delta T here. We've replaced Q with C, M, and delta T here. Furthermore, we know that to get the change in temperature of a substance, we take the final temperature minus the initial temperature. That will give us the change in temperature, or delta T. So wherever we see delta T in this formula in purple here, we can replace it with T final minus T initial, and that's what we see in orange right here. We've replaced delta T with this expression here, T final minus T initial. And so this formula right here in orange is going to be the formula that we're going to use to solve this problem right here. So let's go ahead and do that. Let's see here. What this is telling us is that negative specific heat of the metal times the mass of the metal times the change in temperature of the metal, which TF minus T initial, is going to be equal to the specific heat capacity of the water times the mass of our water times the change in temperature of the water, or TF minus TI for our water. And so now what we can begin to do is plug numbers in from this formula here. If we take a look, the specific heat capacity of our metal is 0.900. And when we're working with this formula, we can go ahead and leave these units out until the very end. Our final answer will be in degrees Celsius. So we'll just leave off these units for now. Times the mass of our metal. The mass of our metal is going to be 45.9 grams times the final temperature minus the initial temperature of the metal, which is 356 degrees Celsius. We're going to set this equal to the specific heat capacity of water, which is 4.18, times the mass of the water, which is 253, times T final minus T initial. The initial temperature of this water is 15.2 degrees Celsius. So there we go. And so now we take this number here times this number here, and we'll get negative 41.31 temperature final minus 356. And this is going to be equal to these two terms multiplied together, which is 1057.54 temperature final minus 15.2. And so now what we need to do is we need to distribute this. We need to distribute this to this term here and this term here. And we need to distribute this to this term here and to this term here. And if we do that, we'll end up with negative 41.31 T final plus, why is it a plus? A negative and a negative. Whenever you're multiplying, that should be a positive. 14,702.8, and this is going to equal 1057.54 times the final temperature minus 16,074.6. And so what we can do now is we can begin to combine like terms. It looks like we can add 41.31 TF here to this side. What we do to this side, we have to do to the other side. We're going to add 41.31 TF here. And when we do that, we are going to end up with 14,702.8 equaling 1,098.84 times the final temperature minus 16,074.6. And so now what can we do? We can add 16,074.6 to both sides of this equation. And we're running out of room here, so we'll try to put this over here now. It looks like we will end up with 1,098.84 times the final temperature equaling 30,777.4. And so now how do we solve for final temperature? You guessed it, we divide both sides by 1,098.84. And we're going to end up with a final temperature of 28.0 degrees Celsius. 28.0 degrees Celsius is going to be our final temperature. So to recap, if we add 45.9 grams of aluminum at this temperature here to 253 grams of water at 15.2 degrees Celsius, the final temperature of this water is going to be 28 degrees Celsius. In this second example, it tells us that we have 31.21 grams of an unknown metal at 97.2 degrees Celsius. We're going to add this to 125 grams of water at 23.1 degrees Celsius, and the temperature of the water is going to increase to 25 degrees Celsius. We have to calculate the specific heat capacity of the unknown metal, and then we need to determine what the metal's identity is. So there's a lot going on here, but essentially what is happening is this. We have a piece of metal, right? We have a piece of unknown metal that we're adding to 125 grams of water. This metal is really hot. It's at 97.2 degrees Celsius. And when we put this metal in this water right here, the temperature of the water is going to increase to 25 degrees Celsius, and the temperature of the metal here is going to decrease to 25 degrees Celsius. They're going to level out at 25 degrees Celsius. And so what we need to figure out is what the specific heat capacity of this metal is. And so once again, we know that the amount of energy that the water absorbs is equal to the amount of energy that the metal is going to lose. So negative Q equals positive Q. The amount of energy lost by the metal will be equal to the amount of energy absorbed by the water. And so we know that we can replace these Q's here with C times M times delta T for the metal and C times M times delta T for the water. And then we can substitute in the value or the expression for delta T, TF minus T initial. And so we're going to use this formula in orange here to solve this type of problem. And so if we take a look, we know that the negative specific heat value of the metal times the mass of our metal times the change in temperature of our metal is going to be equal to the specific heat capacity of our water times the mass of our water times the change in temperature of our water. And in this problem, we're asked to solve for the specific heat capacity of the unknown metal, right? And then we're going to determine the identity. So the way that we do this is by dividing by negative mass of metal times delta T of metal. And what we do to one side of our equal sign, we have to do to the other. So we'll divide this by negative mass of metal times change in temperature of our metal. And so the formula that we are going to use to solve this problem is going to be the specific heat capacity of the metal equaling the specific heat capacity of our water times the mass of our water times the change in temperature of our water, all divided by the negative value of the mass of the metal times the change in temperature of our metal. And so all these values here can be found in our little word problem. So here we go. Let's just start substituting in values. We're going to do this over here. And so to get the specific heat capacity of our metal, we have to take the specific heat capacity of water. You should have that memorized. That's 4.18 joules per gram degrees Celsius. Times the mass of our water. The mass of our water is 125 grams. Times the change in temperature. What is the change in temperature of our water if it's going from 23.1 to 25? Well, we take the final temperature minus the initial temperature. And if we do that, we could probably do that in our heads, we will get a temperature difference of 1.9 degrees Celsius. And then we're going to end up dividing this by, the negative value. The negative value of the mass of the metal. The mass of our metal here is 31.21 grams. Times the change in temperature of our metal. So let's figure out what the change in temperature of our metal is. To get the change in temperature of our metal, we take the final temperature minus the initial temperature. The final temperature of our metal is 25.0, right? That is the same as the final temperature of the water. They're going to level out. Minus the initial temperature, which is 97.2. And we'll end up with a temperature difference, or a temperature change, of negative 72.2 degrees Celsius. So that is our change in temperature of our metal. So we are going to multiply this by negative 72.2 degrees Celsius, right? And so if we take a look, we'll put this in parentheses here. What we will end up with when we put this in our calculator is we're going to end up with 992.8 on top. And it looks like we are going to end up, on the bottom, we will end up with a negative 2,253.4 grams times degrees Celsius. Grams degrees Celsius, right? And so because we have a negative over a negative, that's going to become a positive. And so we have 992.8 joules over 2,253.4 grams degrees Celsius. And when we put this in our calculator, we should end up with 0.441 joules per gram degrees Celsius. So we just figured out our specific heat capacity of this unknown piece of metal, and what we can now do is refer to a table of specific heat capacities of different metals, and we can find the value that is closest to 0.441. And if we take a look at nickel's specific heat capacity, the specific heat capacity of nickel is equal to 0.440 joules per gram degrees Celsius. So we have a really close answer here to nickel. So it looks like this unknown piece of metal here is going to be nickel. So that is calorimetry in a nutshell. If you like what you see, go ahead and click that little bomb in the bottom right hand corner. That's going to subscribe you to my channel. And feel free to leave any comments or questions down in the comment section down below. And I really hope you guys found this helpful.